Problem number 1. Prove that if the span of these vectors is equal to our vector space V, then the span of these vectors, so V1 minus V2, V2 minus V3, all the way to Vn minus 1 minus Vn, and at the end we have Vn. So the span of those vectors is also equal to V. So let's show that this is true. Assume that the span of these vectors is equal to V. And now we have that these vectors, V1 all the way to Vn, belong to the span. And now, since span is a vector space, it is closed under addition and scalar multiplication. Thus, we have that, for example, this difference over here, which is just equal to this sum over here with the inverse element. Well, this is so scalar multiplication, this is addition, so this belongs to the span, since V1 belongs to the span, minus V2 belongs to the span, so their sum, i.e. their difference, also belongs to the span. And using the same reasoning, we conclude that V2 minus V3 belongs to the span all the way to Vn minus 1 minus Vn. So we have that these vectors belong to the span. Well, that means whatever linear combination of vectors, of those vectors I make, that also belongs to our span. So we have that whatever linear combination of these vectors, it belongs to the span. That means that the span of these vectors over here is a subset of our original span. And now we would like to show that our original span is a subset of our new span to show that these two sets are equal. So to show that, we observe that, well, Vn minus 1 minus Vn and the vector Vn, they belong to our span, to our new span. And again, due to it being closed under addition and scalar multiplication, we can add up these two vectors, and then we get that, for example, Vn minus 1 belongs to our new span. Repeating that reasoning, we conclude that Vn minus 2 belongs to the span, and so on all the way to Vn. So all of these vectors belong to our new span. That means that whatever linear combination of those vectors we form, that linear combination also belongs to our new span, thus showing that our original span is a subset of our new span, and now we combined 1 and 2, so this relation here and this, from which it follows that those two spans are equal, hence our new span is also equal to V. So that would be problem 1. Problem number 2. Prove that if this list of vectors is linearly independent in V, then so is this list constructed via the differences of these vectors, similar to problem number 1. So let's assume that this list is linearly independent in V, and let's just take our new list of vectors and form our linear combination and set that equal to 0. And now we just multiply and tidy this up a bit. So we just multiply out the scalars with the vectors in the brackets, and then we group the appropriate terms together. So I group everything that belongs to V1, I group everything that belongs to the vector V2, V3, and so on, and we get this expression. And now using the fact that V1, V2, all the way to Vn are, well, linearly independent, it follows that these scalars have to be equal to 0. So we get that A1 is equal to 0. And then we get that A2 minus A1 has to be equal to 0, but we know that A1 is equal to 0, so we get that just A2 has to be equal to 0. And we repeat that reasoning to get that, for example, from A3 minus A2, we get that A3 has to be equal to 0. And we go this way all the way to An equals 0. So we have that we we set this linear combination equal to 0. We got that the scalars have to be equal to 0. Well, that means that these vectors over here, so this list of vectors is linearly independent in V. So that would be problem number 2. Problem number 3. Suppose that this list of vectors is linearly independent in V, and let W be some vector from V. Prove that if this list is linearly dependent, then W has to be in the span of the original list. So let's show that this holds. First, due to our original list of vectors being linearly independent in V, we know that each of these vectors is different from the 0 vector. If any of them were equal to the 0 vector, then the list would be linearly dependent. So that can't be the case. Now, if W is the 0 vector, then this list over here would just equal our original list, contradicting the linear dependence of this list. So if we want this list to be linearly dependent, then W cannot be the 0 vector, so we know for certain that W is not the 0 vector. Now, if V1 plus W is equal to the 0 vector, then, well, we're done. W is just equal to the inverse of V1 then, and we would have that W belongs to the span of our original list. So let's suppose that V1 plus W is different from 0. Well, now we fulfill all of the conditions for the linear dependence lemma. So we have a linearly dependent list of vectors, and the first element is different from 0. The linear dependence lemma tells us that there exists some index j such that Vj plus W belongs to the span of all the vectors that come before it in the list. So we know that Vj plus W is equal to some linear combination of these vectors. So these scalars are guaranteed to exist by the linear dependence lemma. So now we just multiply all of this and we transfer every term with W to the left side and everything else to the right side. And we pull out the W's out of here to get this. And I will call this here, this expression in the parentheses, which is a scalar, I will label that to be alpha. So W times alpha is equal to this. And now, if alpha were to be equal to 0, then we would have that this over here, which is a non-trivial linear combination of vectors from V1 to Vj, would be equal to the 0 vector, which contradicts the linear independence of our original list. So if this were equal to 0, then that would mean that some smaller subset of these vectors in here were linearly dependent, which is impossible due to the whole list being linearly independent. So however I take my subset of the vectors in here, they're also linearly independent. So alpha cannot be equal to 0. Now that we've established that alpha is different from 0, then we can divide both sides of the equation by alpha to get that W is equal to this. That means that W belongs to the span of these vectors. That also means then that this span here is a subset of our original list. So that means that W belongs to the span of our original list, as we had to show. Problem number 4. Suppose m is a positive integer, so 1, 2, and so on, is the set consisting of 0 and all polynomials with coefficients in f and with degree equal to m a subspace of the vector space of all polynomials. So let S be equal to the union of these two sets. So we got all our polynomials of degree, 1 or 2 or so on, some positive integer, and 0. If we didn't include 0 in here, well, then this set wouldn't be a vector space, because if we look at all polynomials of degree, for example, 1, while 0 does not belong to that set. So there would be no way for this to be a vector space, hence why we have to add 0. And now take P and Q from S and some alpha from our field. And now we ask ourselves, does P plus alpha times Q belong to S? Well, if both polynomials are equal to 0, then the sum is equal to 0 and it belongs to S. If one of the polynomials is equal to 0 and the other is different from 0, well then P plus alpha times Q in this example, because I picked P to be equal to 0, we would get alpha times Q. And now if alpha is equal to 0, well then this would be equal to 0 and 0 belongs to S. And if alpha is different from 0, then we again just get that this is a polynomial of degree m, so it would also belong to S. And if both polynomials are different from 0, then again the sum, again if alpha is equal to 0, well then this would just boil down to P, which is a polynomial of degree m. And if alpha is different from 0, then this sum, again, when you group the terms, is still a polynomial of degree m, so it belongs to S. So in all cases, this always belongs to S. Hence, we can conclude that S is a subspace of the vector space of all polynomials. Problem number 5. Prove that f to infinity, which is the set of all sequences, so just sequences of infinite length, so a sequence of example, just 1, 1, 1, and so on, all the way to infinity, 1 repeating, and any other sort of sequence you can imagine, is infinite dimensional. So the way I've decided to show this, well, if this set was finite dimensional, if this vector space was finite dimensional, then all its bases would be of the same finite length. But here is an example of a basis for this space, and it is of infinite length. It is not finite. Hence, f to infinity, the set of all sequences, cannot be finite dimensional. That means that it has to be infinite dimensional. Yeah, that would be problem 5. Problem number 6. Prove that the real vector space, consisting of all continuous real-valued functions on the interval 0 to 1, is infinite dimensional. So, the vector space of all polynomials is infinite dimensional. Let us limit ourselves to the vector space of all polynomials that are defined on the interval, on the closed interval 0 to 1, denoted by this. So this is how I will denote that set of polynomials. So this is a vector space and it is infinite dimensional. So here's the standard basis. So it's an infinite basis. So this space is infinite dimensional. And now let S denote the set of all the continuous real-valued functions defined on the closed interval 0 to 1. Now, polynomials are continuous and they are real-valued functions. Thus, our set of all of these polynomials that are defined from 0 to 1 is a subset of S. Now, if S were a finite dimensional vector space, then its dimension would be equal to some n, some positive integer. And we'd have that the dimension of our set of all polynomials would have to be less than or equal to n. But this contradicts the fact that our set of polynomials is infinite dimensional. Thus, S cannot be finite dimensional. So it has to be infinite dimensional. Problem number 7. Prove that V is infinite dimensional if and only if there is a sequence V1, V2, all the way to infinity of vectors in V such that This list, so from v1 to vn, is linearly independent for every n from the natural numbers, so positive integers. So let's show that this holds. Let v be infinite dimensional, then v is definitely not equal to the empty set, and v is definitely not equal to the vector space that only has the zero vector in it. So that means we can take some vector v1 that's different from 0. And now, due to v being infinite dimensional, the span of v1 is definitely not equal to v, so the difference between these two sets is non-empty. And now take v2 from that difference of sets, and in general we take vn to be an element, a vector from v without the span of all the previous vectors we've picked. So again, due to the dimensionality of v, we have that this difference will always be non-empty. Thus we get our sequence of vectors. And now, due to how we pick our v's, whatever n I decide to end the list at, that list will be linearly independent due to, well, vi is such that vi does not belong to the span of all the previous vectors, so these vectors just can't be linearly dependent due to us picking vi to be a vector that does not belong to the span of all the previous vectors. So this list will always be linearly independent, no matter how big of an n I pick. So that's one implication. And now the other implication. So let's assume that v is such that there exists a sequence of vectors, so an infinite sequence of vectors in v, such that whatever list I pick of length n, it is linearly independent for each n. And now, if v was finite dimensional, then, for example, the dimension of v would be equal to some m, which would be either 0 or some positive integer. And now, and every linearly independent list of vectors in v would be of length less than or equal to m. But from our assumption, it follows that we can make a linearly independent list of vectors in v of arbitrary length. So whatever m the dimension of v was, we could make a list that is like m plus 1 or m plus 2 and so on. So we can always make a list of linearly independent vectors that's larger than the dimension of v. So v cannot be finite dimensional. We would have a contradiction if it was finite dimensional. So it must be infinite dimensional. And we've proven both implications. So this equivalence holds. So this is one way to test whether a vector space is infinite dimensional. Problem number 8. Let U be the subspace of R to the fifth defined by, so U is equal to the set of all of these 5 tuples, where the first coordinate is 3 times the second coordinate and the third coordinate is 7 times the fourth coordinate. And we're tasked to find the basis of U. Well, so we take an element from U, so a 5 tuple, and due to how U is defined, we know that this is equal to this. So the first coordinate is 3 times the second coordinate, and the third coordinate is 7 times the fourth coordinate. Hence why we have this equality. And now we just decompose this. So I write it as this sum over here, and then I pull out the scalars. So I pull out x2 here, x4 here, and x5 here. And now we see that every element in U can be written as a linear combination of these vectors over here. And these vectors are obviously linearly independent. So these vectors span U and they're linearly independent. So that means that the set of these 3 vectors is a basis of U. Problem number 9. Prove or disprove there exists a basis of this set, so the set of all polynomials of degree 3, such that none of the polynomials p0, p1, p2, p3 is of degree 2. Well, here is an example of such a basis. So the polynomial 1, z squared plus z to the third, and z to the third. So these vectors span this space, and they're all linearly independent. Hence, we've proven that there does exist such a basis by providing an example. Problem number 10. Suppose that V is finite dimensional with dimension V equal to n. Prove that there exist one-dimensional subspaces U1 all the way to Un of V such that V can be expressed as a direct sum of those subspaces. So, due to V being a finite dimensional vector space of dimension n, we get that there exists a basis, so some basis B of vectors V1 to Vn. And now let's define U1 to be equal to the span of V1 all the way to Un being equal to the span of Vn. And now we have that when you sum up these subspaces, you get V. And now all that's left to show is that these do in fact form a direct sum. So take U1 from U1 and Un from Un and set this sum equal to 0. And now, due to the way we define the u's, we have that every ui can be written as some scalar times its appropriate vector vi from the basis b. So when we use that fact, we get that this sum is equal to this. And now, due to b being a basis, all of these vectors are linearly independent. So it follows that the scalars alpha 1 all the way to alpha n all have to be equal to 0. And when we plug them back into here, we get that u1 is equal to all the way to un is equal to 0. So the only way to express the 0 vector using these vectors from our subspaces is by taking the 0 vector from each subspace. So that means that the sum of our subspaces is a direct sum of our vector space V. Problem number 11. Suppose that V is finite dimensional and that U is a subspace of V such that the dimension of U is equal to the dimension of V. Prove that U is equal to V. Well, due to U being a subspace of a finite dimensional vector space, U is also finite dimensional. Thus it has a basis B of U, and the dimension of U is less than or equal to than V. Now we can extend that basis of U, so B of U, to a basis of V. But since the dimension of U is equal to the dimension of V by our assumption, that extension is trivial. There is nothing to add. There is nothing to expand. So B of U is already also a basis of V. Thus, U has to be equal to V. Problem number 12. Suppose that P0 all the way to Pm are polynomials in the space of polynomials of degree m, such that each of these polynomials, when you plug in 2 into them, is equal to 0. So 2 is the 0 of each of these polynomials. Prove that the list of all of those polynomials is not linearly independent in this space of polynomials of degree m. So suppose that this list is linearly independent. The length of that list is m plus 1, and the dimension of Pm of f is also equal to m plus 1. Thus, this list of vectors of polynomials is a basis of our space. Thus, there exist scalars alpha 0 all the way to alpha m, such that, for example, we can express this polynomial over here, so z to the mth, which is a polynomial in our space, we can express it as a linear combination. Due to this being a basis, there exist these scalars such that the sum is equal to this polynomial. But now when we plug in z equals 2, we get that, well, the left-hand side is equal to this. I plug in 2 into each of my polynomials, and the right-hand side is equal to 2 to the m. So due to 2 being a 0 of each of these polynomials, we have that the left-hand side is equal to 0, the right-hand side is equal to 2 to the m, which is impossible, so a contradiction. Hence, this list is not linearly independent after all. We started off with the assumption that it is linearly independent and got a contradiction. So it is not linearly independent, hence it is linearly dependent. Problem number 13. Suppose that u and w are subspaces of R to the 8th, such that the dimension of u is 3 and the dimension of w is 5, and that the sum of these two subspaces is equal to the whole vector space R to the 8th. Prove that the intersection only contains the 0 vector, so the intersection of these two subspaces. Well, the dimension of the sum of these two subspaces is equal to this. And we know that u plus w is equal to R to the 8th, so the dimension of R to the 8th is equal to 3 plus 5 minus the dimension of the intersection of the two subspaces. So we get 8 is equal to 3 plus 5 minus the dimension of the intersection. And well, from here we get that the dimension of the intersection has to be equal to 0. Hence, the intersection has to be of the following form. It is the vector space that only contains the 0 vector. Problem number 14. Suppose that the dimension of the subspace U is 5 and the dimension of W is 5, where U and W are subspaces of R to the 9th. Prove that the intersection is, well, not of the following form, so it is not the vector space that only contains the 0 vector. Well, due to the dimension of u being 5, there exists a basis, so b of u, of these 5 vectors. Now, if we attempt to extend bu to a basis of our whole vector space R to the 9th, using vectors from w, so due to w being of dimension 5, it also has a basis. So in the best case scenario, if I were to extend the basis of u to a basis of R to the 9th using these vectors from w, we can get to the following basis of 9 elements. And then we'd be left with, for example, w5. Doesn't matter, you can always label it properly, but in this case, so let's just go with w5 is the one that's left over with. So now b is a basis of R to the 9th. So if we were to add w5 to it, it would become a linearly dependent list. And v5 can't be gotten from any of these vectors, so w1, w2, w3, w4, due to those being the vectors of the basis of w. So all of these vectors plus w5, they're all linearly independent. So when we add w5 to this list, it has to be in the span of the vectors u. So when we add w5 to b, the list becomes linearly dependent, and w5 can't be gotten from this list since the basis of w is, well, a linearly dependent list. Thus, w5 has to be from the span u1, u2, u3, u4, u5. Thus, when we take the intersection, at least in the best case scenario, the intersection would be this one-dimensional set. It can be even greater, but in the best case scenario, it would still be one-dimensional. So there's no way for it to be equal to the zero-dimensional vector space of the vector space that only contains the 0 vector. So the intersection cannot be equal to this. Problem number 15. Prove or give a counterexample to the following. So, is it true that if we want to calculate the dimension of these subspaces, so when I add up 3 subspaces, is this the correct formula? Does this hold? Well, it turns out that it doesn't hold. So here's our counterexample. So here's one subspace, U1, this line. And then here's another subspace, U2. And here's the third subspace, this line that goes through the origin. So the dimensions of U1 is 1, of U2 is 1, and of U3 is 1. The dimension of the intersections, well, it's just the 0 vector, so it's 0, and the dimension of the intersection of all of the subspaces is also 0. And now when we try to calculate using this expression, so we can see from this example that the dimension of the sum of these subspaces, so when I sum up these subspaces, I end up with the real plane, so r squared. So the dimension of the sum of these subspaces is 2. Now, if we use this expression over here, the right side, so f, when we plug in the numbers, so we get 1 plus 1 plus 1 minus 0 minus 0 minus 0 plus 0. Well, we get that f gives us 3. So we know that the dimension of this sum of these subspaces is 2, and f is telling us that it should be 3. Well, 3 is not equal to 2, so we've just provided a counterexample to show that this does not hold. Problem number 16. Prove that if V is finite dimensional and U1 all the way to UM are subspaces of V, then the dimension of the sum of all of those subspaces is less than or equal to than the sum of all of their dimensions separately. So due to all of these U1 to UM being subspaces of V, which is by our assumption finite dimensional, all U1 all the way to UM are all finite dimensional. Thus, they all have some dimension. So U1 has dimension little U1 and so on. Thus, there exist bases B of U1 all the way to B of UM. And now take the vectors from those lists and form a new list B. Now, if B is linearly independent, then it is a basis of the sum of all of those subspaces. And the dimension of that sum is equal to, well, the sum of all of their dimensions separately. Now, if B is not linearly independent, then we can remove vectors from it until we end up with a basis of the sum of subspaces. Thus, the dimension of the sum of subspaces is, in this case, strictly less than the sum of all of the dimensions separately, concluding that the dimension of the sum of subspaces is less than or equal to than the sum of dimensions separately in general. So when we unite both of the cases, we get that this is what generally holds, where equality turns out to hold if the subspaces are, well, they form a direct sum. So when we glue up all of their bases together, we still get a linearly independent list. So that means that the sum is also a direct sum.